little bit more welcoming for you. All right, so chapter 3. Chapter 3 deals with matter primarily, matter, phases of matter, different types of matter, mixtures, compounds, elements. It deals with something called percent composition as well. Okay, so if we look at matter, let me get that guy out of the way. Matter is anything that has mass and takes up space. And we classify that matter into categories. The main category is matter, has mass, occupies space. Those are the two qualities for that. Things that aren't matter, the energy, so like the rays from the sun, okay, that sort of thing.
We have more different. One for Annika, one for Risa, and one for Anne. Are there people in here?
Yep.
Okay, come on.
Annika's right in front of you.
Oh, okay.
And Brisa's right behind her. Allie, can you go between? And then I think that's yours. Yeah. She goes by Sophie, but.
Oh, okay. And Sophia. Yeah.
Thank you.
Yep.
All right. So like I was saying, anything that has mass and occupies space is matter. We break matter down into two different categories then. Pure substances, and we'll get into why they're called kind of pure substances. And then mixtures, which are mixtures of these pure substances. And we're going to talk about what the difference is between a pure substance and a mixture in a couple minutes. If we look at that in terms of a particulate view, you can see that the elements are all of the same color and shape. For a compound, we're going to take two of those elements and bring them together and see how they're touching like that. That means that they're bonded together. Okay, so that's a compound. And then a mixture is going to be something where we have two or more of these elements and or compounds together, but they're not bonded to one another. Okay, so this is not bonded to that. And then a heterogeneous mixture over time will settle out. So you probably have like orange juice with pulp in it. Anything that says shake before using is typically a heterogeneous mixture. Hetero means different, and it has to do with particle size. And this diagram doesn't do a kind of a stellar job of explaining that. But typically the particle size is very large in at least one of the components. Okay. And one of those is going to end up settling out due to gravity over time. Okay. So sand and water, for example, that is a heterogeneous mixture. That sand would sink to the bottom, just like in the ocean. It's at the bottom of the ocean, right? As opposed to the salt water there, where the salt is going to stay mixed in that water. The salt water would be homogeneous. The salt particles and the water are approximately the same size, and they're very small particles. And so because of that, they're able to stay mixed in with one another. Okay. Now there also has to do stuff called solubility and different things like that we'll get into why things don't stay mixed when they're other sizes, like oil and water. Okay, they're both liquids. You're like, why don't they stay mixed?
Attention all juniors with last names beginning with A through K. Please come down to the LMC if you do not have an ID. That's juniors with the last names A through K. Thank you.
So we'll get into more of why certain things like that don't stay mixed as the year proceeds. Okay. Why is this not changing slides? All right, this is something that you need to add to your notes. So you have something off to the side. You have that spot off to the side. This is a test question. I will tell you right now it's on the test, but I didn't have it in your notes before when I printed these. So make sure you get this in your notes. Okay, so mass is a mixture is the measure of an amount of matter in a substance. So mass is the measure of an amount of matter in a substance. So that's a vocabulary word that you need to know for the test. What I did was I already printed these notes, and then I was making my notes, and I'm like, oh, I forgot to add a couple things. So there's a couple slides in here that are going to be different color background, and you need to add that to it. Okay? Because I'm like, if I, I want to make sure that anytime I give you a test that I've covered that material in the notes, that you have it printed out on there. Okay? So in this case, I didn't get that in there. This should be, I would hope, a vocabulary word that you would have had from another class already. But just in case, I want to make sure that you've had exposure to it. Okay? Because a lot of people are coming from a lot of different places, and it's hard to know if we've all gotten the same thing or not. All right. There are 118 known elements on that we have. All of those are listed on your periodic table. So your periodic table has an ordered list, and they are listed from smallest to largest by the number of protons in the element. So our modern periodic table has the number that is given there, which is 118. If we were on element 118, that means that it's got 118 protons. Hydrogen has 1 proton. So the atomic number, the whole number that's on your periodic table indicates how many protons are in that element. And I think you guys have heard of protons, neutrons, and electrons. Those are the 3 things that make up your atoms. Yeah? Okay. All right. So I gave you a periodic table at the beginning of the year. You pick that up on your way in. Hopefully everybody has a copy of that. So they're all listed on there. One of the things that you need to start getting in good practice with is writing those symbols properly. Okay. So for example, the symbol for cobalt is CO. You need to make sure that your C is bigger than your O for cobalt. Okay. So your first letter is a capital letter. Your second letter is a lowercase letter. And if you're like, well, I always write in uppercase letters and I just write the lowercase ones smaller, like I would write sodium like this, I'm going to mark it wrong. Okay. You have to write it in A. Okay. That is the symbol for sodium. I told you this is a picky class. This is one of the places that I'm going to get you. Now, why is that important? This is cobalt. This is a metal. Okay. If I write this like this in chemistry, I don't have cobalt anymore. I have carbon monoxide. Okay. So it makes a difference in chemistry land, the way that we write things. So you have to, it's like going back to elementary school where they were doing handwriting and you had to do your A's this way or you get marked off. You're back to that. Okay. So despite what you want to do and that sort of thing, you're just going to have to kind of get used to it. And I'm sorry, I know it's ridiculously picky, but that's kind of what chemistry is. Ridiculously picky. Anybody who goes to see a medical professional, a doctor, for example, they sat through the same course, okay, either here or in college. And they have this same indoctrination as far as the way you write things and everything. So, and medical professionals, you want them to be super picky, right? So this is kind of their first step into that. So if you're thinking about going into that profession, just realize that that's something that you're going to be kind of welcomed into. All right, so this is what your periodic table, very similar to what your periodic table looks like. We have our elements listed here. The elements on this side of the periodic table are metals. On this upper corner, they are non-metals. And on my periodic table in class here, you can see that there's a dividing line that goes between these. That's your dividing line between your metals and your non-metals. Okay? And we'll get into more about the periodic table when we get into the next chapter of class. But this is just kind of the first step into that. These are called your average atomic masses. This is called your atomic number, and that tells you the number of protons. Okay? All right, this needs to get added into your notes. The vertical columns. Vertical is this way, up and down. It's like a tower. And then your horizontal columns are called periods. So your vertical columns are called groups or families, and the horizontal ones are called periods. Make sure that you add that into your notes somewhere. Again, test question. I guarantee this will be on the test. Movie are they watching next door?
Moana.
Moana? I have my mouse in here. Here it is. All right, good with this one?
Yes.
Still writing? All right, there's my mouse is working. Maybe this will help me toggle through a little bit better. All right, like I said, elements are made up of these protons, neutrons, and electrons. All elements of the same element have the same number of protons. Example, hydrogen and helium are both elements. All hydrogens have 1 proton, heliums have 2. Okay, compounds then. When compounds of the same element combine, they're still referred to as elements. We have primarily 7 of those. Okay, and you will get used to these if you look on your periodic table. You have 7 of them. You have hydrogen. You have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They form what number here?
7.
7. There are 7 of them. We call them Brinkelhoffs.
The Hoff-Brinkels.
That's how you remember what they are. And like I said, they do make the number 7 on your periodic table. I have 4 different ceiling tiles in here with the Brinkelhoffs on them. So if you forget, you can look up, and there's 2 over here. There's 1 in the middle, and then there's 1 right up above Owen here. Okay? So anytime that you see these written as themselves, you will always see them with, for the most part, a 2 down here, meaning that they're bonded together. Okay? And you've probably seen this when you had biology last year, when you were doing the photosynthesis formula. They always had your C6H12O6, and then they had O2 here. That's what you're breathing in all the time. Okay, so those are called your Brinkelhoffs. Okay, when 2 or more different elements combine chemically, then they're in a fixed ratio, and that new substance is called a compound. So that fixed ratio, it's always that way. So for example, you have water is H2O. You have hydrogen peroxide is H2O2. So you add in an extra oxygen, you get a completely different material. Okay? This you need to drink lots of. This you drink and you're going to be puking up your guts. Okay? That's what they tell when your dog eats over a pound of chocolate over the weekend. That's what they tell you to give your dog to induce vomiting. It's been a long weekend. They also have very different properties compared to the elements that make them up. Okay? So here, the properties of these elements are going to differ from one another. For example, we have sugar. That's the glucose that I was just talking about in photosynthesis, or that's produced in photosynthesis, that when you go through cellular respiration, you're going to use. Okay, so this is your sugar. Okay. Carbon by itself is graphite or diamond. So carbon is either the stuff that's in your pencil that you're writing with right now, or it's diamond. Okay. That's very different from sugar, right? I try to chomp down on a piece of diamond and I'm going to break my tooth. Diamond's one of the hardest substances known to man. Okay. Hydrogen is a clear gas. That's what they had the Hindenburg filled with. Do you remember the balloon, the dirigible, the blimp that burned up? Do you remember that? Seeing that online? It's like black and white footage of the thing back in the early 1900s. Oh, the humanity! The guy yells out. You guys don't remember seeing this stuff? I'll just see if I can pull that up. You know, it's very flammable. Oxygen, clear gas, not flammable, but supports combustion. You need that for fire. We combine those together, we get sugar. Okay? Think about these two things. Flammable, supports combustion, and yet we use this to put out most fires. Okay? These two are gases at room temperature. This guy is a liquid at room temperature. This guy is a solid at room temperature. So they combine in very different ways to give you very different things with different properties. Okay? The only way to separate these compounds is to go through a chemical change. So we're going to talk about chemical and physical changes later on this week. And the only way to separate them is to go through some sort of chemical change to get them back out and break those bonds. These are bonded together. See over on the board, I got compounds over there drawn. Okay, those lines in between them represent bonds. And you have to break those bonds to be able to get them separated. Mixtures can be separated into their component parts. And they have a variable composition. I don't know if this exact slide is in there or not, but I just kind of throw it up here to kind of show you about their variable composition. They can be separated from their component parts, and we can use physical means to do that. You might do that in the kitchen where you have a macaroni noodles, okay? And you use a sieve to separate the water and the macaroni noodles, right? You might do that when you're eating your Skittles and you have a manual separation where you pick out all of the orange ones and the green ones and the yellow ones and you eat those first. Because you have to say the best for last, right? Which is the reds. Red Skittles are the best. No, reds. Purple are right up there. That's why I eat those next. And then the red you save for the end. So, see?
Red and orange, which are the best.
Properties of the substances that make them up are similar to the properties of the substances that created them. So when we talk about salt water, we can have salt water that's 5 grams of salt and 500 grams of water. We can also have salt water that's 50 grams of salt and 100 grams of water. They're still the same thing. They're still salt water. This is just going to taste a lot saltier. But yet there's still a mixture. Their amounts can vary as opposed to your compounds where they can't. You change the ratios in a compound, you no longer have that compound. You have something different. Just like this, H2O, H2O2. Completely different compounds. Good? All right. How can we separate these out? And they talk kind of in detail in there. This is just one of the ways is filtration. So you might have used, like I said, a sieve to separate noodles out. Coffee filters work the same way. Strainer, if you have like a thing that you put over a pot and then just strain it with one little strainer thing.
Attention, Craig. Students, all juniors who do not have a physical ID, please report to the LMC at this time. That's any junior without an ID. Thank you.
Okay, so filtration. We'll be doing a filtration process in our lab coming up next week. Distillation uses the differences in boiling points. So when you boil something, if you start out with like salt water in here, you can boil that water. It's going to leave the salt behind because the salt has a much higher boiling point. The water will evaporate and turn into a gas. When it turns into a gas, then it's going to run through this tube. It's going to get shuttled down through here. The tube has something around it that's cold, and it causes it to condense back into a liquid, and then you end up with pure water over on the other side. This is also the way that they do alcohol, like grain alcohol, when the stuff that people over 21 consume sometimes. That's the way that they do this, and they'll call it, these things they call a still oftentimes, but it's a distillation process. This is very similar also to the way that oil refineries work. So oil refineries get in something called a crude oil. If you've ever heard of crude oil, that's what they get out of the ground. And it's a mixture of a bunch of different stuff in there. And each of those components has a different boiling point. And so when they take it to a refinery, they'll heat it up to a point. One thing will come off as a gas, and they capture that. And then they'll boil it a little more at a higher temperature, and that next component will come off, and they'll capture that as a gas. And then they keep doing that until they get to just the end product and probably just throw that away or do something with it. I don't know. But each grade of oil or each grade of gas that comes off of there is collected in a similar process at a refinery. Chromatography, you might have done something, speaking of Skittles again, or M&Ms. This is often a kind of a experiment that they do at the elementary level, middle school level, where they'll take a piece of coffee filter, they'll put a little bit of wet the Skittle and get a little bit of that dye, food dye on there, and then put it in water. And then as the components move up, certain ones will get left behind at a different spot. And that's called chromatography. And if you take AP, we get into why that happens and how that happens and everything. All right, crystallization. This is another process that is oftentimes done at the elementary, middle school level, where you'll make this rock candy, and that sugar material crystallizes out. So that's another way of doing this. Sublimation. If you've ever seen one of these room fresheners that has a solid component to it and a gas component. And if you let this sit over time, it'll sublime or turn into directly from a solid to a gas. And then it carries that scent throughout the room. And eventually all that's left behind is this like hard solid thing. And then you toss the thing and get a new one. So decanting. We talk about this process quite a bit in here. We do this several times throughout the year. If you have oil and water mixture, you can decant or pour off the less dense item. Manual, like I said, your Skittles, because you gotta eat the yellows and the greens first, because those are the worst, and then eventually you get to the reds. Magnetism. They use a magnet to remove magnetic objects from a mixture. This is the way a lot of the recycling, commingled recycling works nowadays. They'll have a roller here, and it'll have a belt on it, and they end up pulling the magnetic objects out, like your aluminum cans and that sort of thing, and then leave behind the other stuff to separate another way. All right, so when we talk about mixtures then, remember our chart at the very beginning. We talked about homogeneous. Those are also known as solutions. So that's another word for that. I think they put that in, I think that's in your notes. If it isn't, make sure that that is in there. That homogeneous are called solutions. Okay, I can almost guarantee that's a test question. So homo, the prefix homo means the same. So when we talk about homogeneous, we mean that these are all the same particle sizes, are very similar, and they're very small. And because of that, they're able to mix together and stay combined. Okay, so here are some examples of some of those things that have a constant composition throughout. Heterogeneous does not blend well, and they are going to settle out over time. Hetero means that they're going to have different size particles, and some of those particles are going to be very large. So we have suspensions that are sand and water that are going to settle over time, and then we have stuff like colloids. The colloids then will show what's called a Tyndall effect. And that's something that you're probably not familiar with the terminology, but you're probably familiar with the concept. Okay. So, have you ever, has anybody taken driver's ed yet? Okay. Or maybe you talked with your parents, the rest of you. What do you do in the fog with your headlights? Right? What else, what should you not do with your headlights in the fog? Put them on bright. Okay, so don't use your brights, even if it's dark outside. Don't use your brights when it's foggy. Okay, and the reason why you don't do that is because of this thing called a Tyndall effect. When you shine a light through one of these colloids, you will end up reflecting and refracting that light back into your eyes. Okay, so let me see if I can find picture of this images. So this is like the Tyndall effect. See how the light is kind of reflecting back through. Let's see if I've got a better understand. Oh, it's over here. Nope, I need to grab this one. There we go. All right. Here's kind of an example of the way it looks in, like if we were to shine a laser light, see how it internally reflects within that. See with the headlights how it's going to end up, it almost makes it look brighter. And it ends up reflecting that light back in your eyes, and then you can't see real well. So you should never use your brights. It's not because it's going to bother the other people. It will. But the primary reason is it actually disrupts and makes it, your vision worse as far as being able to see ahead of you. And that has to do with the Tyndall effect. So here's another good example of the light internally reflecting. So if it's a positive Tyndall effect, it means that it's a colloid. Okay. Where are my notes? Here they are. Yep. It's a Monday, you guys. Seems like every Monday's like this to me. All right. So what kind of matter is baking soda? What do you think?
Solid, right?
It's a solid, yep. Is it an element, compound, or mixture? Compound, okay. How do you know that it's not an element?
Because it has multiple different types.
Right, it has multiple elements in it, so it can't be a, it can't be an element. It's written as a chemical formula, which means, so it's written as a chemical formula. When it's written as a chemical formula, it means that it has a set ratio of one component to another. Remember, mixtures don't have that. They can be variable. But when you have multiple elements and they are in a set ratio, then you know that you have a compound. So multiple elements and set ratio. That makes sense? Anytime you see a chemical formula where there's more than one element in it, that should also be kind of a bells going off that this is a compound. All right, we do. see if you can figure out here for a second or two. You add water, salt, and sand to a bottle and shake it. What type of matter is present in the bottle? Is it an element, compound, heterogeneous, or homogeneous? What do you think? Take a second to try to figure that out. All right, what you think? Thoughts?
It's a mixture, a heterogeneous
Yep.
mixture.
It's a heterogeneous mixture. Somebody else tell me why they think it's a heterogeneous mixture. Merrick?
Because the sand would disperse from the water.
Right, it's going to settle out over time. Yep. Okay, that makes sense? So the sand's going to settle out over time. So because of that, it's going to be a heterogeneous mixture. You can kind of visualize that happening, right? I mean, like I said, the ocean's kind of an example of that, right? All right. We do number 2, particle diagram. What type of material is present here? Let me move the, oh, shoot. Stupid thing. Let me move this. Maybe. There we go. Okay, that's a better picture. What do you think?
Is it a homogeneous mixture?
Is it even throughout?
No.
Somebody else want to give a guess? Hetero, right. Yep. So it's going to be heterogeneous. Okay. This is settled out over time. It's down at the bottom. Okay. This is an element of some sort. Okay. It's all the same stuff. And then this would be one of those diatomic elements, one of your Brinkelhoffs. Okay. The next section then is states of matter. And this is the one that I think we can probably go through pretty quickly. So states of matter, there's 3 states of matter that we study. We study solids, liquids, and gases. If you've geeked out and you've decided to go on the YouTube and look about other ones, there are other states of matter out there. There's plasma, there's this Bose-Einstein condensate. If you want to nerd out, go on YouTube. There's plenty of videos out there on these. But the only 3 that we deal with are solids, liquids, and gases. Okay? Solids then are going to have a definite shape and volume. Okay, so if you have something solid, it has a shape that you can describe and it has a volume that you could measure as well, just from its components. Okay, they are typically linked here. You can kind of see this dashed line kind of linking them together. Those are called intermolecular forces, or IMFs. We will get into those later this year, but they are going to be what hold the solid together and hold the particles close to one another. Okay, they kind of link them together.
Students, any sophomores with the last name beginning with A through K, please come to the LMC if you do not have an ID. That's any sophomores with the names beginning A through K at this time. Thank you.
Liquids then take the shape of their container. So whatever container they're in, they're going to take the shape of that container, but they have a definite or fixed volume. So their shape is variable, but their volume is fixed. Okay? Or definite. Their intermolecular forces are a little weaker than in a solid, but they're still close to one another. There's still some attraction between those molecules, and that's what's going to keep them That's what's going to keep them closer together. Okay. So liquids have a little bit weaker than solids. Because of that, they have the ability to move or to flow. Okay. So gases then take the shape and volume of their container. They are very far apart, so they spread out as far away from one another as they can. They move in straight lines until they hit stuff. And if they're hitting the walls of the container, that's what's going to cause them to have gas pressure on that container. So when you have a bicycle and you're filling up the tires in your bicycle, it usually talks about pounds per square inch or PSI. You fill it to a certain level. And that's the pressure that those gas particles are exerting out on. Okay. Phase changes are called physical changes. They're not going to change the identity of the substance. So if you have water that's in ice form and you melt it, it's still going to be H2O. If you turn that into steam, that steam is still going to be H2O. And I'm fairly certain you guys have probably seen most of these vocabulary words as far as changing between. So if you go from a solid to a gas, that's called sublimation. That might not be a term that's key in your brain. So that may be one that you need to commit to. If you go between gas and a solid, that's called deposition. Again, these two, I'm guessing, you might not have kind of run into over the years. But the rest of these, I think you're fairly comfortable with. Gas to a liquid is condensation. That's like the dew on your grass in the morning. And then vaporization can be either boiling or evaporation. Then if we go from a solid to a liquid, that's melting. And liquid to a solid is called freezing. Water that then is going to freeze remains the same chemical substance. The only thing that's changed is how those particles are arranged. Are they attracted to one another or not? The energy that particles have due to their motion is called kinetic energy. And temperature then is a way of measuring that kinetic energy. Okay. As we move across here, from a solid to a liquid to a gas, we're going to increase the distance between the particles. That's why liquids and gases are able to flow. They're called collectively fluids. These are fluids because they can flow. They can change their shape. They have increasing potential energy. They have increasing temperature and increasing kinetic energy. All right, if a substance fills this container, it is completely and takes the shape of the container, what state of matter would it be?
Solid. No, wait, it takes the shape of the
Yep, it takes the shape of the container and it's filling the whole thing.
liquid. No? Gas.
Gas, yep. So it's going to, if this was our container, you would have particles here, 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 and they're going to spread out as far and wide as they can get from one another. Okay? What is the name of the phase change from gas to solid?
Deposition.
Deposition. This deposition, an example of that, is where you go, you get frost on your windows in the morning, in the wintertime. It would have gone from the humidity or gas in the air and deposited right on your window without going through condensation phase. And then what phase of matter is shown down here?
Solid.
Solid. Okay. Everything's together. It's not spread out at all. There's attractions between those particles. All right. Given the following image, what phase is this guy in?
Liquid.
He's a liquid. Okay, he's all down at the bottom here. We have some attraction between these particles. What's the phase change that occurred if that liquid was to be cooled? What phase change would we go through?
Freezing.
Freezing. Okay, and then predict what this substance would look like if we were to heat it. What's going to happen to this liquid if we heat it?
It's going to become a gas.
Yep, so we're going to spread out, and those particles are going to spread out around and throughout. Is that all that we do, or is there another slide? Yeah. Oh, no, we're done. Okay, so you have, you do is tonight and for 3-1 and 3-2.